I was like,
before we get into
and
it.
then, it's like so phenomenal. Go out of his brain. And I was like, what happened? No, somebody just said,
Do you know? Supposed to be Friday.
well, I
we're
didn't
practicing
know.
on
I got to get ready.
Friday, we're practicing.
Oh my God.
All right. We're going to continue with our packets. We just have one big topic left to do, and that is solving equations. We'll spend the next 4 days just going over these types of solving equations. But I feel like a lot of it we're prepared for all this. We've seen, we've worked with double angles. We've worked with expanding terms. We've worked with unit circle. We've worked with factoring.
That's something that we do. I stand right at the
I don't care to live. I just have to see my kids. Okay, I could get back.
Okay, so if we can turn to page 16.
I'm gonna play that like a rugby.
Okay, you have access to your unit circle at the back page, so you can refer to that if we need to go back and forth between it. Okay, so starting with number 1. It says find all the solutions to the equation on the interval from 0 to pi. So again, page 16. All right, so we never want to try to cancel any variable or trig terms out. We want to hold on to all of our variables so we can find all the solutions. So we're looking at 2 terms here. We can think in terms of factoring, right? What's the GCF that we can take out of both these terms here? Cosine x, okay, so we're going to take cosine x out. So if cosine x comes out, we're essentially dividing by cosine x. So what remains? First term, cosine goes away, we're left with 2 sine x. And if we remove cosine x, what's left here? Good, -1, right? Not a 0, make sure it's 1. Okay, so now that we have 0 showing on one side of the equation and everything is factored, we can find our solutions from both sets, right? We can set cosine of x equal to 0. We can set 2 sine of x -1 equal to 0. And now we're going to look for all of the solutions that land on the unit circle. Okay, cosine of x equals 0. And 2 sine x -1 equals 0. Okay, let me just clean this up as far as I can go here. I can add 1 to both sides. Okay, so you can refer back to your unit circle or just try to recall from memory. Where is cosine going to be equal to 0? Oh, radians. We're going to do everything in terms of radians here. Where's cosine equal to 0? Pi over 2. Anywhere else? 3 pi over 2. So we have two solutions from cosine of x. How about from this one here? Sine of x equals 1/2. Where's sine positive? Yeah. First and which quadrant? So variation of the power over 6. Where else? Yeah, first and second quadrant, right? Sine is positive in the first and second quadrant, ASTC. Okay, any questions there? All right, try number 2, same process. Take the GCF out, factor, and then set both parts equal to 0. Okay, try number 2. Okay, what'd you guys find as your GCF? 10x, okay. Divide tangent of x out of both terms. You got that 0 showing on the right side, and now you can set both parts equal to 0 and look for solutions from both trig terms. All right. Everybody good so far? Okay, where's tangent equal to 0? 0 and pi. We don't include 2 pi because in our domain, 2 pi has a parentheses around it, so that means it's not part of our domain, but 0 and pi are, so we keep 0 and pi. Okay, 1 over root 2, this may not be as recognizable, but 1 over root 2 is the same thing as what? Root 2 over 2, right? That feels more familiar. You can rationalize the denominator to make it look more familiar to identify from the unit circle. Okay, so which quadrant is cosine going to be positive? 1 and 4, right? 1 and 4. Positive cosine, ASTC. All right, so x equals and 7 pi over 4. Okay. Okay. Any questions with 1 and 2? All right, number 3, can you identify what the first step of number 3 is? Good, subtract 10x. We don't want to divide by 10x. If you divide by 10x, we're losing that variable. We don't want to lose that variable, so yeah, make sure that you hold on to everything. So the way we do that is we bring it over to one side, get that 0 to show up, and then go from there. Okay. Same thing with 3 and 4, so see how far you can get with 3 and then go to number 4. right? GCF first. Mhm. Okay, two sets of solutions, one from tan x, one from that sin x squared minus 1 equals 0.
How does that, tangent x not get rid of the, wouldn't that just end up leaving sin squared x?
Oh, well, I factored a tangent x out, so I need to hold on to tangent of x. Is that what you're asking? Yeah, I'm dividing the tangent x out so that I know what to leave inside the parentheses, but I still want to hold on to that GCF. Okay, so anybody, what can we do to make this go? What's our next step to try to square root? Okay, now what do we have to be careful about with square root? What's going to show up in front? Good, plus or minus. Okay, careful about that, plus or minus. Okay. Tangent is equal to 0. We know that from the previous problem at 0 and pi. All right. Where is sine going to be 1 or negative 1? Pi over 2 and 3 pi over 2. Yeah. Okay. Questions with 3? All right. Approach 4 the same way that you did number 3. All right. Subtract. Don't divide.
Will you always find two x values?
Are we always going to find 2 x values? Yeah. For these problems, yes. Are you asking about like 2 sets of solutions? Yes. Yeah. For the most part, we are. We are going to come across where one set's going to give you undefined and the other is the only one producing solutions. But yeah, usually we're going to have 2 sets that we're finding from. Okay, check your first step. Yeah, go ahead. Okay. You should have gotten sine x equals 0 and tan x equals plus or minus 1. All right, where's sine going to be equal to 0? 0 and pi. Oh, Josh, to answer your question, maybe you're asking about whether everything will produce two solutions. I think sometimes we may have less, sometimes we may have more. So in this case, yeah, we have all four quadrants are represented, right? All the power of 4 variations will show up. Okay.
But usually never less unless it's undefined.
Yeah, that's right. Yeah. Okay, 5 and 6 should feel easier. You can go almost directly into just taking the square root and then start looking for your solutions. Just make sure that plus or minus will show up. Okay, so try number 5 and then try 6. Yeah.
For tangent, are you always going to be dealing with all four quadrants?
Only if depends. In this case, we are, because tangent is equal to 1 at power of 4 and 5 power of 4, and a negative 1, 3 power of 4 and 7 power of 4. So it just depends on the problem.
Okay.
So in this case, it looks like we have all four solutions, all four quadrants represented. Number 5, go directly into taking the square roots. Okay, look at your unit circle values. Where is tangent of x going to be root 3? Good, all the variations of power 3, right? Y over x, root 3 over 1, that's going to be pi over 3. Plus or minus, so all four quadrants will be represented. Okay, number 6 will feel similar. Just make sure you divide the 2 first before you jump into the square roots. Now this may not look like a unit circle value, but see how far, see if you can keep cleaning up that right side and identify something that looks more recognizable. Okay, square root of 1/2, the same thing as what? Same thing as root 2 over 2, right? You know root 1 is just 1. And then if I rationalize that denominator, I can get it to look like root 2 over 2. So if something doesn't look recognizable, then keep working at it and see if you can get it down to something that you can find on the unit circle. Okay, all the variations of what I've had before. Okay, whenever you're ready, second page, page 17. Yes.
How are you able to multiply by?
We can always rationalize the denominator, right? So if I have a radical in the denominator, I can always multiply the top and bottom by that radical to get it to look like a different form, right? We're not changing anything because we're multiplying by 1, so we can always do that. Okay, so page 17 says find all solutions. So the only adjustment we have to make here is we'll have to do a plus 2 pi n, where our n is an element of an integer. So we'll talk about that in a second. But the difference here is that now we're dealing with 3 terms, which is going to be factoring. Okay. Is everybody good on this page? So if it helps, if you see a square term, a linear, first degree term, and a constant, we know we have to go through factoring. If it helps, maybe you want to just solve an easier problem. So I'm going to factor an easier problem here. I'm going to do 4x squared minus 4x plus 1 equals 0. Right, so if you want to go through star method, you can. Some of you are able to jump directly to factoring using cosine. That's perfectly fine. But I think for a lot of us, it just helps to pretend like this is an easier problem to kind of work our way up. Okay, multiplies to be a times c, adds it to be -4. So if you think about 2 values that multiplies to be 4 and adds it to be -4, we'll think of -2 and -2. Right? Reduce the fractions. This becomes -1/2. Pull the denominators out in front. Now that we have factored form, we can bring the x back to in terms of the original variable cosine. Both parentheses are the same, so we can just solve for one parentheses, and we know we'll get duplicate answers on the other side. Okay, so where is cosine going to be 1/2? X equals pi over 3 and where else? Mm-hmm. Now notice that it says find all solutions and it doesn't specify a domain. So we just have to make sure that we say plus 2 pi n, where n is an element of an integer. So if we want to find all the variations of pi over 3, we can just plus 2 pi n, and that just means that we're adding and subtracting all the variations of 2 pi, because we know that these values will keep repeating itself. Okay, questions with 7? Say it again.
Repeat the 2 pi n.
So it says find all solutions. So that means it's not just restricted to between 0 and 2 pi. So we have to be able to say that, because all our values keep repeating themselves, right? So we just say plus 2 pi n to indicate that if I say pi over 3, it continues infinitely in both directions. So it could be minus 2 pi n, minus 4 pi, minus 6 pi, and this just indicates that, n can be infinite number or can be an integer. As long as n is an integer, we can represent all the possible values just by saying that. Okay, try number 8. If it helps, maybe you want to factor an easier problem in terms of x, and then bring sine back into the fold and go from there. Thank you. Okay. Okay, sine x equals to -1. And where's sine going to be -1/2? Which quadrants? 3rd and 4th. Variations of pi over 6, right? Yes.
Did you get 3 pi over 2?
Oh, we ask ourselves, where is sine equal to -1? So pi over 2 would be +1. 3 pi over 2 would be -1.
Okay.
Right, the y value for sine for 3 pi over 2, -1. Okay, number 9 should feel pretty, oh yeah, let's talk about number 9 here. GCF, but there's going to be something a little different with one of our solutions. Okay, GCF first. Okay. So sine is equal to 0, that's pretty apparent, 0 and pi. So this here,
Have to see my counselor at a meeting.
Okay.
I got this.
okay, sine of x equals 2. What's strange about this? Undefined, because your sine graph is only going to oscillate between what? -1 and 1, right? Think about your parent graph for sine. It's just going to hover between -1 and 1. It's never going to reach 2. So this is undefined. Okay, questions with 9. Okay, what's strange about number 10? Sine and cosine, right? Everything we've done before has been just one trig function, right? Either all cosine or all sine. So that's what we would like to have happen. Everything in terms of one trig function. So is there anything that we can do to make it into one trig function? Trig identities. Okay. What can we do with one of them? Which one is easier to change? Mm-hmm. The Pythagorean identity, right? Sine squared plus cosine squared equals 1. Rearrange that equation and find a replacement for cosine squared x. So recall. If I solve for cosine squared x, that's equivalent to 1 minus sine squared x. I'll take it. I guess it's huh? No, you don't have to. All right, let's make our substitutions so we can get everything in terms of one trig function. Okay, is everybody clear as to why we're taking these steps? All right, so so now once you get everything cleaned up, push everything over to one side of the equation, and then it should feel like number 7 or 8 where you're factoring and going through those steps. We want to solve an easier problem. Do this factor in terms of x. Okay, what do you know about sine x equals -2? Undefined. First and second quadrant. Questions? Okay. Finish off 11 and 12. Give you guys 5 minutes. I will show the answers. But they're both factoring problems. Number 12, it looks messier with that sine x to the fourth, but factor the same way, but now instead of x and x, it's x squared and x squared. Okay, so just factor like you normally would. Just have to raise the power a little bit higher. And after I go through the answers, I'll come around and check off page 16 and 17. Okay, so we're just doing this for the next few days. We're going to bring in double angle, but if you feel good about this, you have a good foundation, and we're just going to be adding a little bit to it each day. But if you know how to do this, you should feel pretty good about the next few days as well. Make sure all of your terms are on the same side of the equation so that you can go through your factoring. 11 is actually going to end up looking like number 10. Instead of x and x, we're now x squared and x squared because of x to the fourth. We're going to have trouble with one of these equations. So there's a double issue here. First, you can't take a square root of a negative. But even if that were positive, square root of 3 will still be outside the range, right? Square root of 3 is more than 1. So it's still outside the interval from -1 to 1. So whether it's -3 or +3 or root 3, we're not going to be able to get anything out of it. We're sine 1 or -1. Pi over 2 and 3 pi over 2, okay.